dietary proteins can be used to make body protein. This is really the main reason why we consume protein. We don't really consume protein to use it as fuel, because our other macronutrients are way better at that than protein, okay? Carbohydrate and fats we can use as fuel better than we do protein, although we do use protein sometimes as fuel if it's in excess or if it's really needed. But the main reason why we look at protein quality and we discuss different types of protein and quality, etc., is to make sure that our bodies can produce all the proteins that we require based on the foods we consume. So again, it depends on 3 particular criteria. We have amino acid content, so how much is in the actual food. And I've already shown you by these tables that sometimes plant proteins contain a lower gram amount of protein than other animal protein sources. That's just a fact and a feature of the food itself. So that's something to note. That can affect the quality. The digestibility is another key factor. Okay, so how our body actually digests the protein that you consume, and there are differences between plant and animal sources. For example, animal proteins tend to be better digested than plant proteins, although plant proteins are pretty good, maybe not at the level that animal proteins are, but they get quite up there, which is good. But one of the reasons why they don't get absorbed as well or as readily as animal proteins is because they contain these anti-nutrient molecules. So these are things like phytates, oxalates, and fiber. And they're just, again, features and factors that are contained in plant protein foods, primarily because they're there to ward off predators and to allow the plants to grow naturally in the wild, etc. So these are just some nutrients that can trap other nutrients and impede the absorption of various micronutrients or even amino acids, for example, that our body needs. Okay, so plant foods contain these things called anti-nutrients that we have to consider when we're looking at plant food quality. Right? Amino acid composition is another one as well. So it's not just about the content, but what amino acids are contained within the content. What proportion of essentials does a particular protein source have? Because that's really what we're going after. The highest quality proteins have the greatest proportion of essential amino acids because those are the ones our bodies can't make. And there are differences between sources of animal versus plant. We get into this notion of limiting amino acids, which are essential amino acids that are supplied in less than the amount needed for protein synthesis. And some protein sources have limiting amino acids that do just that. They limit the ability of the plant protein source in particular, when eaten on its own, to build new proteins. But there are ways around that. It's important for us to understand these limitations with respect to plant protein so that we can do things to augment the quality of the plant protein, which we'll talk about. Okay, so again, complete proteins contain all the essential amino acids. We're really focused on the essentials when we talk about quality because, again, those are the ones our bodies cannot make and we need to get from the diet. Incomplete proteins are missing one or more essentials, and in some cases they're harder to digest because of the presence of anti-nutrients. So plant proteins generally are of lower quality for all of those various reasons. So they contain less available amino acids, they have a greater impact of limiting amino acids, and they have the presence of anti-nutrients. And this is not to say plant proteins are useless. We can still digest 70 to 90-ish% of the protein that we consume from plants. But again, as I said, context is important. And if we are consuming a plant-based diet, we're getting all of our protein from plants, whole foods in particular. We just need to know and understand that these are some of the limitations. Okay, so again, here's another definition of protein quality. The ability for the body to use the protein source to synthesize new proteins, and what we call that is the anabolic potential of the protein source. And here's a table on this slide dias. And these two classifications are used to classify different protein sources. Now you don't need to memorize these numbers, okay? Don't worry about that. But you should know what PDCAS and DIAS are. So PDCAS is protein digestibility corrected amino acid score, and DIAS is digestible indispensable amino acid score. So these are scoring systems that rate the proteins against one another to give you an idea of protein quality. Kind of analogous to the glycemic index. Just talking about, glucose-containing foods and how readily they release glucose into the bloodstream. This is the situation for amino acids. And you can see here the varying degrees of scores that we have. So when we look at this upper portion, and you can see what they refer to in the table below, but these are all protein isolates or protein concentrates, even plant protein isolates and concentrates, okay? So not from the whole foods. And we see that the quality is really high. It's higher, right? They're at the top of the list. PDCAS only goes up to 1, so anything that's labeled 1 is considered high, or the highest. And DIAS goes a little bit above 1. But you can see that these protein concentrates are isolates, right? Even pea protein concentrate. Yeah, even that one is in the 0.8 range, so it's relatively higher. But we'll talk about what the concentrate isolate versus the whole food is in a moment, for sure. But if you look down this list, it's not surprising then that we see things like almonds, chickpeas, tofu, corn-based cereal, collagen is 0, right? So these protein sources have lower quality scores according to the PDCAS and the DIAS, based on those main criteria that we talked about in relation to their essential amino acid content. And this column over here, limiting amino acids, this just tells us which of the essentials are the main limiting amino acids in the different foods. Now, there's always going to be a limiting amino acid. There's always going to be one that is in less concentration than all the others. Even if you're talking about whey protein, which is one of the highest quality proteins. But if we look at this figure on the right over here, and we note these dashed lines across, these are the recommendations, or this is the amount of the amino acid that we should be consuming. So again, even though there's a limiting amino acid, the gray bars represent animal protein sources. You can see them down over here. The white bars are plant protein sources. For all of the, and I'm only showing you methionine and lysine because those tend to be quite limiting in some of them. But you can see here that despite the fact that, perhaps milk protein isolate is limiting in methionine, the animal protein sources still reach that threshold. So the limiting amino acids don't really have an effect in the animal protein sources. In the plant protein sources, on the other hand, you can see that for several of them, and here's total essential amino acids, they actually fall below the line of what is needed to sustain protein synthesis. So for methionine in particular, there's a lot of foods, a lot of plant protein sources that are deficient in methionine, which is an essential amino acid, and this limits their quality dramatically. Okay? So that's what this figure is showing us over here. A little bit more about incomplete protein. So legumes, type of plant protein, they grow in a pod. Peas, beans, garbanzo beans or chickpeas, black-eyed peas, peanuts, soybeans, etc. They tend to have limited amino acids of methionine, tryptophan, and cysteine. And you can see that in the previous slide that I showed you. And I put an asterisk beside soy, because soy protein is, for all intents and purposes, considered one of the highest quality plant sources, and some would say that it's a complete protein. Their limiting amino acids aren't so consequential. Okay, so it's a good plant protein source to consume. In terms of incomplete proteins, we have nuts and seeds over here, and they're limited in isoleucine and lysine. These are two other essentials. And then similarly, grains and cereals, so rice and grains, wheat, etc., they're limiting and also limiting in isoleucine and lysine. So the legumes are limiting in different ones, like methionine, and the grains are limited in other ones, isoleucine and lysine. Okay, so this is where we get to this notion of how we can overcome these issues with plant proteins. And one of the ways to do that is this idea of protein complementation. So this is where you combine two plant protein sources, you eat them together, and your stomach doesn't know. It's just digesting everything. So at the end of the day, you end up with a full complement of amino acids. Okay? Now, the amount of protein you consume is still going to be an issue because plant proteins are less. But in terms of the complement and how that affects quality, you can combine plant protein sources, eat them together, and achieve your full complement to support protein synthesis. All right? So here's an example. We have rice, as I showed you, that's deficient in lysine. We have beans that are deficient in methionine and cysteine. Remember, beans are legumes, right? Rice is a grain. You combine beans and rice, and you get your full complement. Okay, and so you look at some of these pictures, and to me, it's no surprise that, lots of cultures around the world, in places where perhaps they don't eat as much meat, or they don't have access to as much meat, have dishes that have been, you can trace back years and years and years, where they combine rice and beans together. Right? So here's just a few of them. In South America, in Africa, in the Middle East, etc., they have, lots of dishes where they combine rice and beans together, and these are staple dishes in these countries and cultures. So perhaps it's because they've figured out that they've thrived on consuming these foods together because they provide the full complement of amino acids. And maybe I'm giving them too much credit, but I have read this actually in history books that look at nutrition and trace nutrition over the years. And I don't think this is any coincidence that several different isolated, cultures and groups around the world have come up with dishes combining legumes and grains. Here's another figure that I found that I thought was also interesting to note, and it brings us back to the very first lecture that I gave you with that table that I created. But here's another one, again, just for context. You don't need to memorize numbers. This is just for context for you. And again, it's protein per 100 grams, which is about 3.5 ounces. So the same as what I showed you in the very first class. And you can see plant-based proteins versus animal-based proteins. When you're looking at these, it's important to note the usual serving size that one would consume of a plant or an animal-based protein source. 3.5 ounces for meat is fine, that's right. Maybe you even consume more, 6 ounces, right? That's normal. But is it normal to consume 3.5 ounces of peanut butter or almonds or things of that nature? So remember I alluded to this in the very first class. So when you're looking at protein content, of course 28 grams for 100 grams for peanut butter is on par with what you would get for some other meat sources, but you don't eat that amount. And the calories in that amount of protein in nuts is very high. So just keep that in mind when we're looking at charts like this. So how do we improve plant protein quality? So this is a really great article. It's a review article that was published in 2022, quite recently. And they're looking at how we can improve the quality of plant proteins that we consume. So we see this Venn diagram over here, and across the top, we have the 3 main factors that I talked about that relate to protein quality. So digestibility, protein content, and composition, right? The limiting amino acids relate to this composition. And so to improve the digestibility, for example, of plant protein sources, there's many things we can do to the legumes and the grains, all right? right? So first of all, we can soak them, we can germinate them. Cooking them breaks down some of these anti-nutrients or cell walls, etc., that release more of the amino acids. Industrial processing, like soybeans processed into tofu, or TVP, like textured vegetable protein, that makes the amino acids more available to us. Using probiotics or digestive enzymes to break down the amino acids or to break down the polypeptides into amino acids in the actual food before you eat it. These are all ways in which we can have better access to the amino acids. Protein content, we can also, of course, increase our serving size, so just eat more of the food, okay? And a way to do that, that overlaps between these two, is to consume protein isolates or protein concentrates, so protein powders. They've actually shown, there's been a lot of research showing that, pea protein, potato protein, things like that, that are isolated and given to individuals, and muscle protein synthesis was measured after exercise, that they show no difference whatsoever. But that's not the whole food, okay? Keep that in mind, all right? As well, in terms of limiting amino acids, we can fortify, so there are some foods out there that actually give back certain amino acids or proteins, and we can do that to certain foods to increase the limiting amino acid content, okay? So we can do that. And also, as I just mentioned, when we're dealing with foods, you can combine foods together and consume them in a single dish. And as long as you eat it together, they're digested and absorbed together, then it's considered a full complement of your amino acids. A little bit of terminology I just wanted to make sure that we all understand in terms of protein supplementation. We have concentrates, we have isolates, and then we have hydrolysates. Okay, so these are three different ways in which we could provide amino acids beyond the whole food. So I found this cool infographic that kind of just lets us know the difference between those. So first of all, we have protein concentrate, which is exactly what it is. It's just a concentrated protein source in the food. So it's taken out of the food, but it also contains other nutrients, perhaps some fat, some carbohydrate. And so if you look at the protein supplement that you take, if you take a protein supplement, you'll see it may say concentrate or it may say isolate. If it's concentrate, it has more of the nutrients, perhaps maybe less of the protein, but still it's concentrated, okay? And it tends to be lower price. And this one is not suitable for people who have problems with digesting protein or who are allergic to milk, okay? And actually, obviously, this figure is relating to milk protein, but you can apply it to any protein. If you have an allergy to protein, milk protein concentrate or any concentrate is not appropriate because the protein is in its intact form. Protein isolate, so it contains a higher percentage of protein and a lower percentage of other nutrients. Sometimes other nutrients are added back, so it depends on the protein source you're consuming, but more often than not, the isolate is just that. It's the protein of the food that's just taken out of the food, just that. So if you want a protein isolate, you're going to just consume the protein, unless it's a particular supplement where nutrients have been added back, and maybe it's marketed as a meal replacement or something like that, okay? And this one is also not suitable for people who are allergic to milk in particular, or the protein food in particular, okay? Because the protein is intact. Then we have hydrolysate, and this is where the protein is broken down already into the amino acids. So it's really fast absorbing, it gets into your system really quickly, you use it very readily, and you can read more about this as well. It's obviously higher in price, but a complete hydrolysate protein supplement is suitable for people with an allergy. Why is this? I talked about this last class. Why would a hydrolysate be suitable for someone with an allergy, but not a concentrate or an isolate? You're allergic to the, dipeptide or tripeptide, the small peptides that can get through. Remember we talked about digestion and absorption? You're allergic to a part of the protein that's intact. You are not allergic to a single amino acid or any of the 20 in isolation. So if you give hydrolysate to someone, it's already hydrolyzed. The amino acids are already broken down, or the protein rather is already broken down into its amino acid constituents. So this is why it's suitable for people with allergies. Of course, consult physician, etc. Be careful about this. But anyway, I just wanted to make sure that we understand the difference between these three. And then this one kind of talks about concepts regarding protein digestion and absorption. Any questions about that before we get into the next part of the lecture? All right, excellent. So, for the rest of my time with you, we're going to be talking about sport and exercise nutrition, particularly in relation to protein. So first of all, one of the big questions that I get all the time from people is, how much protein do you really need? And like anything in physiology, the answer is, it's all relative. It depends, right? This is usually the answer to these questions, but I'm going to tell you why it depends and how we can look at different contexts and kind of figure out that answer for different people, okay? But I'm going to start off by sharing with you the official position of the International Society of Sport Nutrition. Now, this was published in 2017, I believe, so it's quite a few years old now, but I'm still sharing it with you because a lot of the data are still very relevant. There's maybe been a few things that have changed, and I'll allude to that on Friday's class, but generally speaking, this is still the main advice, okay? So I have some links over here to the actual article, if you'd like to read that. Some links to some social media articles that have come out, one of them written by my PhD supervisor, Dr. Stuart Phillips at McMaster University. So we worked together. I was at Mac for my PhD, and I worked with Stu, and he's a worldwide renowned researcher in protein and exercise. And so he has a perspective piece that he put out, and I'd like for you to go and read it. It's really interesting. But spoiler alert, okay? Most dietary protein used for building body proteins, then it's used for energy and other molecules, okay? We can digest a lot of protein, but how much can we actually use at one time to build it? So what he means by that is you can eat a ton of protein. You can sit there and eat protein till the cows come home, okay? All day long, you can just down protein shakes. But is that going to be anabolic? Is that going to be useful to your body? And so there's a lot of research that's gone into the timing and the amount that you actually need, okay? And so these are, again, some of the questions that we're going to be answering over here. And then he also alludes to the fact that we don't store protein very well. We store fat extremely well. We store glucose pretty well, up to a finite amount, and then it's stored as fat. But we don't store amino acids. We have some in our free amino acid pool. And then the amino acids need to be used somehow. They don't get stored anywhere. They're either incorporated into body proteins or they're oxidized or whatever. We went through this last class. We don't store it well, all right? So taking in too much is of no benefit, really. I'll explain. So these are the 7 points of the ISSN, International Society of Sport Nutrition Position Stand. First one, okay? Individuals engaged in regular exercise training require more dietary protein than sedentary individuals. Pretty fair statement. We can all agree on that. I even showed you with the IAAO method last class that, those active individuals, the active males, they required a lot more protein, okay? So this is a well-known fact. Number 2, protein intakes of 1.4 to 2 grams per kilo per day for active individuals is safe and it may improve adaptations to exercise. So this is well above the RDA. And this is a position stand of the International Society of Sport Nutrition. So they're understanding this notion of that the RDA is not for optimal performance or optimal physique, etc. So more is better for these athletes, up to a certain percent, okay? Like up to a certain amount. When part of a balanced diet, increasing protein intakes are not detrimental to kidney function, and they're not detrimental to bone health. Okay, there's been some research out there that has been debunked in that higher intakes of protein in healthy people does not relate to kidney dysfunction. Of course, if you have a kidney issue, that's another story. And then in terms of bone, there have also been some research or some notion that higher amounts of animal protein is bad for our bones because it leaches calcium out of the bones. But that has been disproven using stable isotope technology, which are really intricate studies. So the higher levels of protein are not bad for bone and they're not bad for our kidneys. So while it's possible for physically active individuals to obtain protein requirements or recommendations from food sources, supplements are okay, particularly as we've talked about. If one is a plant-based athlete, they may need to focus on consuming supplements, like isolates or concentrates. Next, different types and quality of protein can affect amino acid availability. So this is our notion about quality. Okay, we talked about that. Number 6, appropriately timed protein intake is an important component because this relates to immune function, recovery, subsequent performance, things of that nature, and of course growth and maintenance of lean body tissue. And under certain circumstances, for athletes in particular, okay, consuming branched chain amino acids may improve performance. This is really the only place where they talk about BCAAs potentially being important, but context matters. These individuals are already consuming an incredibly high amount of protein. Perhaps a little more BCAA is not going to, have any deleterious effect. I still believe it's likely not necessary, but again, this was alluded to in the position statement. For athletes and individuals consuming high levels of protein, not your general population. Okay, so endurance exercise, 1 to 1.6, strength and power exercise, 1.6 to 2. And this was the summary statement in the position stand. Okay, it is the position of the ISSN that exercising individuals ingest a range of 1.4 to 2 grams per kilo per day, so not 0.8, which is the RDA. And then they go on to say individuals engaging in endurance exercise should ingest levels of the lower range, intermittent activities, levels of the mid-range, and strength and power at the high range. And again, this relates to the amount of muscle mass that they need to do their sports. So there was a meta-analysis that was published in 2018, again by Stu Phillips' group, and my colleague Rob Morton was the lead author of this particular study. This is not in athletes, okay? This study was done in healthy exercising adults, mostly untrained adults. First of all, what's a meta-analysis? You guys know what a meta-analysis is? Can someone tell me? Yeah. Yeah, exactly. When you combine multiple findings from different studies together, in this case it's randomized controlled trials, and when you combine RCTs together, the idea is you're able to get a really good idea and view of what the literature shows in its totality. So it's really strong level of evidence, okay? So dietary protein supplementation augments changes in fat-free mass and strength during resistance exercise. So what this figure is showing here, these are the results from the meta-analysis. We have all these studies, okay? We have most of them in untrained individuals and some in trained individuals that were put together to figure out this result. You can see there's JOS 2010. One of my studies is in this meta-analysis as well that I did back in the day, looking at resistance exercise and protein supplementation. But in any case, they graphed all of the changes in fat-free mass for all of these studies here. And they figured out the break point, so it's using similar statistics with the IAAO, although these concepts are a little bit different from one another. In any case, similar stats. And they found this break point to be at 1.6 grams per kilo per day for all of these studies that have looked at exercise and protein supplementation. So they conclude that protein supplementation beyond the total daily protein intake of 1.6 during resistance exercise provides no further benefit on gains in lean mass. And I'm just showing you lean mass, but strength, they found the same thing. And this is because it plateaus essentially after 1.6. Regardless, they found that 1.6, which is double the RDA, is likely the level that exercising individuals, untrained, like me primarily, even older individuals as well, should be consuming at least at that level. But more doesn't really do too much according to the science. But still, 1.6 is double the RDA if one's exercising. So that is what the science actually shows, okay? The next slide is just an infographic of that study. So this is supposed to be put out to the general public to understand the results of the study. So it kind of has some nice pictures, it has this graph in there, it has some final points. I just wanted to throw it in there to remind us all that knowledge translation is really important. It's great for us scientists to do these studies and have it sit in a journal and on PubMed, but unless we disseminate our knowledge through social media or through these types of infographics, posting on social media and talking about it, it's not going to get anywhere, right? So these infographics are created about influential studies to allow us to disseminate our work. So this one was made by another researcher, and it's endorsed by the journal that it was published in. All right, so let's break this down a little bit more in terms of the amounts needed. So the belief is that athletes require very large quantities of protein for optimal athletic performance. Now, I've kind of told you a little bit that that's not necessarily the case. We don't need like grandiose amounts, but athletes do need more. But if you speak to an athlete, they'll say sometimes if they're uninformed that they're very concerned about their protein intake, they need so much protein, blah, 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 okay? And you know what? This may be true for bodybuilders and strongman athletes. What are their goals? To build muscle. That's the only thing that they are concerned about on a daily basis, all the time. I need to eat to build. And they're obviously not taking, testosterone or anabolic steroids or anything like that. It's really amino acids and exercise are the two things that are going to get them the muscle they need, right? So, sure, these types of athletes, they need a ton of protein. But let's do the math, okay? So we have an 80-kilogram male consuming 4,000 calories. So there are some athletes that fall into that. Okay, even if you say 100-kilogram male. In any case, let's just take this example of an 80-kilogram male consuming 4,000 calories because he's a swimmer and he's very active and he swims like 8 hours a day, right? So he needs all of these calories to sustain his exercise. Well, if we do some calculations, if we consume 15% of energy from protein, so if he's consuming protein at the low end of the AMDR, remember AMDR is 10 to 35%, so if he's consuming protein at the low end, that 15%, and he can consume all the way up to 35%, but I'm just choosing 15%, okay? 15% of 4,000 is 600 calories. protein. This equates to 150 grams per day of protein, because protein is 4 calories per gram. So if you do the calculation, you divide it by his body weight, this athlete consuming protein at 15% of his total calories is already close to 2.0 grams per kilo per day. So I'm showing you this because I think it's important to note too, and to not be obsessed or bogged down with this idea that I need protein, I need protein, I need protein, that if you are consuming a lot of calories, because that's what your sport requires, you work with a dietitian, let's say, or you're cognizant of having a well-balanced diet, you are likely consuming enough protein. That's my point here, okay? If you eat a lot of a balanced diet, you maybe don't need to worry and focus on maximizing protein intake, because you probably also need fat, and you need carbohydrates and other nutrients and things to sustain your activity. So just wanted to prove that point over here. So is there a greater requirement for protein? So again, we talked about this in the position stand, but yes, this is true. So for aerobic athletes and for strength athletes, we'll just break it down a little bit. Okay? So aerobic exercise does require more amino acids, perhaps not as much as resistance exercise, because they're not building muscle or they don't want to gain too much muscle. However, they require amino acids for a different reason also. So they need to repair their muscle, of course, after an athlete runs a marathon or whatever the case may be, cycling, like far distances, they get muscle damage, micro damage, muscle soreness, and so we still need to repair muscle, so of course they require amino acids. But aerobic athletes, particularly at the end of a race, or maybe when carbohydrate stores are low, they use amino acids for oxidation. So athletes actually, so these aerobic athletes actually use more amino acids with their exercise than resistance exercise athletes, because they need it for fuel. When the body is functioning at that high intensity for that long period of time, they will take whatever fuel it can get, and obviously you don't want to break down your muscle. So they do require higher amounts of amino acids for those reasons as well, and you need to replenish, of course, once you use. Strength exercise, of course, requires primarily to build muscle and then to repair muscle following exercise. But if you think about the different types of exercise that these athletes do, they both require amino acids, but in different ways. Except, of course, to repair the muscle that's damaged. Okay, so this is the last bit for today. We're obviously not going to get through all of this today. We'll do more on Friday, but I just wanted to start this discussion so that we can start thinking about this. So these are the questions in the next class that I'm going to answer. So how to maximize recovery and repair growth? What amount of protein do we need post-exercise? What's the optimal timing of protein ingestion? And what type of protein should we ingest? And you may have some answers already based on what I've taught you, right? You may already know how to answer some of these questions in the best way for you, which is a goal of mine with this class, okay? But there's 2 more slides for today, but I wanted to start this discussion by bringing it back to the basics of our daily pattern. What happens in a day with respect to our muscle turnover? Okay, so this is a really cool figure that has been alluded to many, many times by those that teach protein nutrition. And it was from a 2009 paper. And it's important to note that our muscle is in constant turnover. And this is the balance, again, between protein synthesis and protein breakdown. So we have MPS, muscle protein synthesis, versus MPB, muscle protein breakdown. And this is, you can consider this what it would be in a day, right? If you eat balanced meals, each meal, then your fed state gains should equal your fasted losses. And then you end up in balance. So you're taking in the amount that you require, but it goes in waves, right? So when you eat a meal, you have an increase in protein synthesis. That's this line over here. And then when you absorb that meal, and you're in a post-absorptive state, similar to glucose, right? Muscle protein synthesis drops off. And then you actually have an area where muscle protein breakdown increases. Then you eat a second meal, and you see this process occurring again. So you have a rise in protein synthesis until you absorb what you need, and then protein breakdown rises. And the hatched line is muscle protein breakdown. You can see it doesn't rise and fall to the same level as protein synthesis. Protein synthesis is much more manipulated by diet and exercise. Muscle protein breakdown is it maintains a standard curve, if you will. We only really see big decreases or big issues with breakdown in disease-related states. Otherwise, it's pretty standard, okay? So we can manipulate muscle protein synthesis. That's where we get to this figure over here. So superimposing the other figure. Again, if you look at the hatch line, muscle protein breakdown, it's the same in both figures. It doesn't really change very much. But what we can manipulate is, let's say you add resistance exercise to the mix. So you add resistance exercise along with a meal, along with eating. What you're doing is really increasing the fed state gains. So you're increasing the percent change of muscle protein synthesis, and you're also decreasing the fasted losses because you have more amino acids and more an anabolic stimulus to the system. And over time, this is the idea that with exercise and with appropriate nutrition, you build muscle. You can apply this concept to athletes, of course. You can apply it to adolescents and youth. And we also use it when we're talking about older adults, right? So the importance of exercise